I'm going to talk about what ordinarily in astronomy is referred to as a Jeans mass. Your textbook refers to it as the mass that can be in balance, so M sub balance. And this relates to star formation and relates to structures that we see in the sky that are in gravitational equilibrium. It could be molecular clouds, it could be nebulae, it could be stars themselves. And the basic idea, what goes into M balance, is let's say I have a cloud, and that cloud, all parts of it are in equilibrium. So there's not a net force acting on any single part of it. That means that all throughout this cloud, if I just take this arbitrary layer with the dashed line, that layer all along it, the weight, so the force of gravity that's trying to make that shell collapse, is canceled out by a force of pressure that is trying to make it expand. And those two forces, being equal strength in opposite directions, just cancel out, so they sum to zero. And it's going to not just be for that particular shell, it's all throughout the entire star or cloud. Now, that pressure is coming from thermal pressure. And that means, and what James Jeans did to first derive this, if it's an ideal gas, you know that pressure is arising from the density of particles that make up the cloud and the temperature that they're at. And then your book goes through and rewrites this in a way to try to make it a little bit more convenient. So you don't have to wrestle with quite so many constants and factors that might not be right on the tip of your tongue. And so you can rework the Jeans mass into the form that's in your book, which just says that I have the mass that can be in balance for my cloud is going to be this factor 18 times the mass of the sun. So it's just a scaling factor. And then under a square root, I have a temperature to the cube divided by the number of density particles. So the meaning of this M balance, let's hop ahead to that. If I have some cloud as a total mass bigger than M balance, the thermal pressure can't support it against its weight, and it's going to start to collapse. If I have a cloud, this total mass is less than this M balance, then the thermal pressure can support it against its weight. All right, so having said that, let's go back up. So as the temperature gets bigger, so the cloud is hotter, it's going to have more thermal pressure, and that will make M balance bigger. As the number density of particles in the cloud gets bigger, that's in the denominator, that's going to make M balance smaller, and that's going to mean that you're more likely for the cloud to be unstable and start to collapse under its own weight. All right, and then what all these terms are, M subscript sun is just your book's shorthand for what's a solar mass, so what's the mass of the sun, 2 times 10 to the 30th kilograms. T is the average temperature throughout this cloud in Kelvin, but don't put any units in there with T. You're just using the pure number part of it. All of the units are here in solar masses, and you don't need to change that into kilograms. Lowercase n is the number density of particles, so there's some cubic centimeter that I'm going to go in and measure and just count how many particles are in there on average. And it's just one number, so we're assuming that, again, that's uniform throughout the cloud. And just like with the temperature, don't keep any of the units of the per cubic centimeter in with the number density, just use the pure number part of it. All right, so let's try a few examples and show what you can do with the mass that can be in balance. So if you look at conditions typical for a molecular cloud, so those we know are the star-forming regions in the Milky Way. Yay. You find that molecular clouds are cold, say about 30 Kelvin, and on the scale of things in the Milky Way galaxy, actually fairly dense. So number density of about 300 per cubic centimeter. So what does that give us for the biggest mass of a cloud that could be in balance between pressure and gravity? When we put in those numbers, I have a 30 cubed over 300, and that's all under a square root. It's going to give me 170 solar masses. So a molecular cloud in the galaxy, if it is less massive than about 170 times the mass of the sun, it's not going to undergo star formation. It's not going to start to collapse. And that's why typically star formation events that we see in the Milky Way are a few hundred stars being made all at once. So you'll have a molecular cloud build up enough mass to exceed M balance. Then it can start to collapse, and then as it starts to collapse, this N in the denominator is going to get bigger and bigger and bigger, which pushes M balance to be smaller and smaller and smaller. So my relatively large molecular cloud is going to fragment into many smaller clouds. So we look up in the sky at night and we see like the Pleiades with a few, say, 100 stars, or the Hyades with a few hundred stars, these open cluster environments. We have star formation making a few hundred stars at a time. It is the gravitational collapse of a typical molecular cloud in our galaxy that's giving rise to that. All right, let's try a couple other examples with it. And let's look at the properties of the first stars. So like literally the first generation of stars. Now before any stars were made, the only elements that are available are hydrogen and helium. Helium doesn't form any molecules under even astronomical conditions. And hydrogen will form a molecule, it's H2, but that molecule is not able to radiate, and so the clouds are not able to cool to form denser, cooler sort of molecular clouds like we have in the Milky Way galaxy. So for that first generation of stars, you're looking at gas that is trapped to be relatively hot. And for the gas to undergo star formation, then, since temperature is pretty high, for it to collapse, you're going to need to have already a fairly high number density. And so early star formation, first generation of star formation, is a very different environment than we have in the Milky Way galaxy today. So something like 300,000 particles per cubic centimeter. So let's see what the mass that can be in balance is for those conditions. So again, 18 times mass of the sun, 200 cubed over 3 times 10 to the 5th, and all under a square root. Go through and calculate that, get that to be 93 times the mass of the sun. So gravitational collapse to form the first generation of stars, we expect it to have made not hundreds of stars at once, but one gigantic star at a time. Because in further collapse, this is already quite dense and is not able to effectively cool. So M balance is not going to tell us that this is fragmenting as it is going to collapse under its own weight. Instead, we're going to get a single massive star. It's a very short lifespan, then exploding as a supernova. Right, and then the last example, I'm going to take our expression for the mass that's in balance and apply it to the sun, because the sun is in hydrostatic equilibrium. So what do we think should be the characteristic temperature of the sun? All right, so now M balance is known. It's 1 times the mass of the sun. It's going to equal 18 times the mass of the sun times temperature cubed over number density of particles, all square root. All right, so I want to get the temperature by itself. 1 times the mass of the sun over 18 times mass of the sun. And then I'll square that to clear the square root. It's going to equal temperature cubed over the number density of particles. And mass of the sun cancels out, top and bottom. And we solve for the temperature by itself. It's going to be the number density of particles over the pure number 18 squared. And I have to take the cube root to get the temperature. Now, if I want to estimate the temperature in the sun, I need to know what the average number density of particles is for the sun. So how are we going to do that? We need to get the total number of particles in the sun and the volume of the sun. So it's going to be the mass of the sun divided by, just for simplicity, I'm going to say that the sun is just made out of hydrogen. And you can look up in the back of your book, one hydrogen atom is going to have a mass of 1.7 times 10 to the minus 27 in kilograms, because they're really small. Kilograms cancel out, and we'll get the total number of particles in the sun, 2 times 10 to the 30, divided by 1.7 times 10 to the minus 27. It's going to be a huge number, 1.2 times 10 to the 57th. Okay, and then to get number density, I also need to know the volume of the sun. Volume of a sphere, 4 pi upon 3 times r cubed. And we want this volume to be in cubic centimeters. So we look up what the radius of the sun is, convert it into centimeters, 6.96 times 10 to the 10th. Cubed. And so give me 1.41 times 10 to the 33 cubic centimeters, because the sun is big. So finally, number density of particles total number of particles over the total volume of the sun. And two things we just calculated. And that's going to give me 8.48 times 10 to the 23 per cubic centimeter. So 1 over centimeter cubed. All right, so I've got N now. We can go ahead and calculate what the temperature is. So remember, cube root 8.48 times 10 to the 23 over 18 squared. And that works out to be 1.4 times 10 to the 7th. That's going to be a temperature in Kelvin. So about 14 million Kelvin. So not knowing much of anything about anything except gross properties for the sun, its mass, its radius, pretty much it's made out of hydrogen, and we could do a little bit better estimate in here. We come up with a temperature of 14 million Kelvin. In fact, the core of the sun is a little bit hotter than that, 15.7 million Kelvin, so almost 16. But this rough estimate for the average temperature of the sun, for it to be in hydrostatic equilibrium between pressure and gravity, is enough to tell us that the sun has to be a nuclear furnace. The hydrogen ignition temperature for densities like we have in the sun is about 10 million Kelvin, so significantly cooler than this 14 million Kelvin. So the sun is a gigantic nuclear furnace.